Every element on the periodic table has a completely different story. They behave differently, they exist in different abundances, and humans have totally different uses for them. One of the most controversial elements, if that's in fact a thing, is uranium. Uranium can provide power, it can cause destruction, and most people really don't understand it. Learn more about uranium, the last of the natural elements, on this episode of Everything Everywhere Daily. This episode is sponsored by SCOTTeVEST. Do you ever have issues carrying all of your electronics? Or do you wish that your clothes had more pockets? SCOTTeVEST has your solution. SCOTTeVEST has a complete line of jackets, vests, pants, and shirts, which have extra pockets to carry the things you need. Getting through airport security is a breeze with a SCOTTeVEST jacket. I know this because I've been traveling around the world for the last decade wearing SCOTTeVEST clothing almost every single day. You can get 15% off all SCOTTeVEST products by going to SCOTTeVEST.com and using coupon code EVERYTHINGEVERYWHERE, all one word at checkout. Once again, that's SCOTTeVEST.com. I'm sure you're probably familiar with the periodic table of elements. The periodic table is a listing of all the elements in order of their atomic numbers. An element's atomic number is just the number of protons it has in its nucleus. The number of protons is the thing that defines what an element is. It starts with hydrogen at 1, helium at 2, and keeps going up through all the elements that you've heard of. The very last of the elements you will find in nature, and hence the heaviest natural element, is uranium. Uranium has an atomic number of 92. There are two natural isotopes of uranium. Both of them are unstable and weakly radioactive, and more on that in a bit. We know that humans were using uranium at least 2,000 years ago. There's evidence of the Romans using uranium ores in ceramics and glasses. One of the uranium oxides is a bright yellow color and does a good job adding color to crafted objects. Uranium is also part of the mineral pitchblende, which was historically used in glassmaking. Silver miners in the Czech Republic would often come across pitchblende when following a silver vein, but only when the vein ended. They gave it the name pitchblende, which basically means bad luck rock. However, none of the people who used these forms of uranium had any clue that there was something called uranium or that there was something known as radioactivity. Uranium was first identified by the German chemist Martin Heinrich Klaproth in 1789. He wasn't able to produce a pure uranium metal, but he did know that the element in the chemicals he created was a brand new element. He named this new element after the recently discovered planet Uranus, which was discovered 8 years earlier. A metallic form of uranium was finally created in 1841, but the substance remained mostly a chemical curiosity. There wasn't a whole lot of use or demand for the substance. In 1896, French physicist Henri Becquerel discovered radioactivity when placing a uranium compound next to some photographic film in an envelope in a closed drawer. Here, I should take a moment to describe the radioactivity of uranium. Uranium is a weakly radioactive element. I say weakly because if you remember back to my episode on radiation, the longer the half-life a substance is, the less radioactive it is. You can think of it like burning something. The faster it burns, the hotter it burns. So too with radiation. The shorter the half-life, the more radioactive it is. Uranium has two naturally occurring isotopes. An isotope is an atom with a different number of neutrons. The two isotopes of uranium are uranium-238 and uranium-235. The numbers reflect the combined number of protons and neutrons in the nucleus of the atom. The half-life of U-238 is 4.4 billion years. The half-life of U-235 is 703 million years. U-238 makes up 99.3% of all the natural uranium, and U-235 makes up the remaining 0.7%. There's a third isotope called U-234, but it is in such extremely small quantities that we can basically dismiss it. The differences between these two isotopes of uranium are really the crux of the story going forward. In fact, if there is one thing that you take away from this episode, it should be the differences between these two isotopes of uranium. In 1939, German chemists Otto Hahn and Fritz Strassmann discovered that when uranium was bombarded with neutrons, the atom actually split into lighter elements. Enrico Fermi, who was working at the University of Chicago, hypothesized that if uranium released enough neutrons when it split, then it could sustain a chain reaction. Later in 1939, he discovered just that. Every time a uranium-235 atom split, it would eject, on average, 2.5 neutrons. Those neutrons could then slam into more uranium-235 atoms, and so on and so on and so on. The problem was, this only worked on uranium-235, not uranium-238. And uranium-235 only makes up 0.7% of all uranium. On December 2, 1942, Fermi created the world's first artificially sustained chain nuclear fission reaction at the University of Chicago, below the stands of the football field. It was also discovered that when U-238 was hit by a neutron, it didn't split the atom apart as it did with U-235. Rather, it would capture the neutron and turn it into a new element, plutonium-239. Plutonium-239 can then be split like uranium-235. An isotope that can be split is called fissile. An isotope that can be converted into an isotope that can be split is called fertile. So uranium-235 is fissile, and uranium-238 is fertile. The power of this chain reaction was the basis of the atomic bomb and the Manhattan Project in World War II. Unlike what Fermi did at the University of Chicago, to make a bomb, you need an uncontrolled chain reaction. To achieve that, you need a lot of fissile material. If you don't have enough, the reaction will be throttled by the non-fissile material. The first of the two atomic bombs used in World War II was called Little Boy. This bomb was a uranium-based bomb that consisted of a lot of uranium-235. Getting this much uranium-235 presented a huge problem. As I mentioned before, U-235 makes up less than 1% of all uranium. Also, I'm talking about these two different isotopes as if they're two different things, but they're not. They're both uranium. They look and act and behave the same chemically. The only difference is that one is slightly heavier than the other. So how do you separate out the uranium-235 from the uranium-238? This process is called enrichment, and it's really difficult to do. It's done today by creating a gas called uranium hexafluoride. This gas is then put into a cylindrical tube that acts as a centrifuge by spinning around. The heavier U-238 will tend to go to the outside, and the lighter U-235 will tend to stay on the inside. As the gases are separated this way, they go through the process over and over and over, until the end result is that the gases have different concentrations of isotopes. This enrichment process is why it's really hard to make an atomic bomb. Both a nuclear reactor and an atomic bomb require enriched uranium. However, there's a big difference between the two. The fuel in a nuclear reactor will be about 5% uranium-235, whereas in a bomb, it has to be 90 to 95% uranium-235. That is why a nuclear power plant, literally, physically, cannot blow up like a bomb. It doesn't have the fuel to do so. So if you enrich uranium to increase the concentration of uranium-235, what happens to the rest of the uranium-238? That's called depleted uranium. Depleted uranium is significantly less radioactive than regular natural uranium, because the part with the shortest half-life has been removed. It has several uses which takes advantage of its extreme density. Depleted uranium is used as an armor in tanks, and it's also used in anti-tank ammunition. In commercial usage, it's often used, believe it or not, as radiation shielding. Because it's 68% more dense than lead, it's often used in medical equipment which emits gamma rays. Extremely dense material like lead or uranium is great for blocking gamma rays. But you might be thinking, isn't uranium itself radioactive? Yes, it is. But if you remember back to my episode on radiation, uranium is an alpha emitter. It's throwing out large helium nuclei, which are very easy to block. The radiation the uranium shielding would be giving off could easily be blocked by whatever the metal casing on the instrument is. In the early and mid-20th century, there was a brand of glazed ceramic dinnerware called Fiestaware. It was noted for the bright colors of its dishes and bowls. Uranium was used in its glazing in some of the colors, especially red, up until 1972. You can still purchase vintage Fiestaware, and yes, it's slightly radioactive. Even though I've talked mostly about the radioactive and nuclear aspects of uranium, I should also mention that it is a highly toxic metal. So radiation aside, it probably isn't something you should be ingesting. I'll end with one final interesting tidbit. I've mentioned that uranium-235 has a much shorter half-life than uranium-238, and that you need uranium-235 to have a nuclear chain reaction. That means billions of years ago, there would have been much more uranium-235. In fact, if you go back far enough, there would have been enough uranium-235 in rocks to get the percentages you need for a nuclear reactor. Could there have been a naturally occurring nuclear reactor? And the answer is yes. There's evidence that about 2 billion years ago, in what is today the African country of Gabon, a natural nuclear fission reaction took place at or near the surface. They can tell by the remnant elements which are left over, which are the telltale signs of a nuclear reaction. It would have been a very weak nuclear reactor, producing maybe enough heat to create a hot spring, but nonetheless, it was a natural nuclear reaction. Something which, given the levels of U-235 in the rocks today, would be impossible. Uranium is a natural element that can be found in seawater, many rocks, and in minute amounts in drinking water. There are probably some atoms of uranium around you and inside you right now as you are listening to the sound of my voice. Uranium gets a bad rap, but that's mostly because people just don't understand how it works and what it is. If you take the time to learn about it and respect it, you will realize just how valuable and important of a substance it can be. The associate producer of Everything Everywhere Daily is Thor Thomsen. Today's review comes from listener Yeet821 over at Apple Podcasts in the United States. They write, "Great, short but fantastic content." Thanks, Yeet821. Short but fantastic review. Remember, if you leave a review or send me a question, you too can have it read on the show.